Okay, so what I want to do here is make a quick video to go over the Hardy-Weinberg equation. And the big thing I want you guys to remember, this is used to calculate the allele and gene frequencies of a population. But more importantly, when we're using this, it's used to measure frequency changes in the population. And if we see a change, then that's an indication evolution is occurring within the population. Now, this works, really, it only works with traits that are dominant and recessive. So it's not going to work if we try to do a pleiotropic or polygenic or any of those traits where you have multiple alleles. This is your straightforward, and I'm start out the example here. Black is dominant to white variation, or whatever we're talking about. This could be fur color in cats. It could be petal colors in flowers. It could be tall versus white. So you really have to think back to genetics when we're talking about Hardy-Weinberg and use the knowledge we gained during genetics to say, okay, now I can apply that into this equation to understand if the population's evolving. All right, so let's start with we're going to walk through just a real easy example, and I want to show you guys how to do these calculations. Let me get my pen going here. All right, so here's an example when we look at Hardy-Weinberg. Let's just keep it simple. I got a population of cats. Give them some whiskers. And in my cat population, I have a dominant variation and a recessive variation when it comes to color. So these cats, we'll say these cats are all white. They have white fur, which is produced by a gene. And these cats have black fur, which is also produced by a gene or an allele. So the black cat, to make it a little easier, I'm just going to shade them in. Or we could say light versus dark, whatever. So you have a bunch of cats running around your farm. And you get them all together, and you take a look at them, and you go, okay, how many of each color do I see? What can you physically see? You're looking at the phenotype of these cats and just making up easy numbers. You have 40 of these black cats and 10 of these white cats. So what you can see is the physical expression, the phenotype. Now, the challenge is in a dominant recessive relationship, any black cat could be homozygous, big A, or they could be heterozygous. So looking at a black cat, I don't know what genotype or what alleles that they carry to be black. I only know they have a dominant A allele. The white cats, however, since we've established this is a recessive variation, I know any white cat will have two little a's. Little a. That's the allele frequency, or the alleles responsible for white cats. So we go back to Hardy-Weinberg equation. P plus Q equals 1. In Hardy-Weinberg, P represents your dominant allele. In this case, P represents the big A allele. Q represents your recessive allele, little a. All right, so that's one part. Now this part of the equation is what gives us, let me type it out so it's a lot cleaner. This gives us allele frequency, okay, which is important. We need to know that. But what we also need to know and understand is the genotype frequency. And this is where we look at P, I gotta do X, okay, P squared plus 2PQ plus Q squared. And this is a little p, not a capital P. Sorry, autocorrect can be a pain when you're working with Word here. Okay, so that equation equals 1, or 100%. Now when we're working with genotypic frequency, or the genotype frequency, let's go back here. This represents big A, big A. That's the genotype. Dominant, homozygous dominant genotype. 2PQ represents the heterozygous genotype. And Q squared represents the recessive genotype, little a, little a. All right, so what we're doing is establishing the equations to use with this population. So we come over here and I look at this and I go, okay, I got 50 cats. 40 of these cats are black. I don't know how many are big A versus big A, little a. I can't look at them and determine that. I just know they're all black cats. The white cats, 10 of them, I know they are little a, little a. I can see recessive color, and I know the genotype that makes them recessive. I can go back to genetics with this. So what I can do is look at these cats, and I can say, okay, 10 out of 50, because there's 10 of these white cats out of the entire population. So 40 plus 10 gives me my 50. 10 out of 50 is 0.2, or we could say 20%. So 20% of my population is little a genotype. That is the same as saying Q squared. So I go, okay, this is my genotype frequency. So you may be asked a problem. Let me, back that up. What is the allele All right, so what is the allele frequency of a population that has 10 white and 40 black cats? Or maybe it says, what is the dominant allele frequency of a population that has 10 white and 40 black cats? Well, we've already established Q squared equals, and again, lowercase, autocorrect, sorry. Q squared equals 0.20, but that tells me my that Q squared tells me my genotype frequency. I now need to figure out how do I take a genotype frequency and turn it into an allele frequency. Well, if Q squared is a genotype, oh, gotta apologize, I don't have this on my keyboard. Hopefully you guys remember algebra. Square root of Q equals allele frequency. Okay, so this is where you pull out your graphing calculators or your fancy calculators, or simply a calculator with a square root function, which apparently my keyboard doesn't have. And I go square root 0.2, ba-dang, keep it simple, two significant figures, 0.45. So the allele frequency, square root of 0.2 equals 0.45. This is the same as Q, which is, back up here, Q is a recessive allele frequency. So if I know Q, remember the equation, P plus Q equals 1. I know Q is 0.45, just basic algebra here, guys. P plus 0.45 equals 1, P equals 0.55. So now the allele frequency of Q, or recessive allele, is 0.45. The allele frequency of P is 0.55. So here's a hypothetical. Uh-oh. In 2020, you measured your population, 0.45 equals Q, 0.55 equals P, and then you watched 2040, 20 years later, you remeasured did the frequency change? So I go back in 2040, I'm looking at the same population generations later, and that is the key with Hardy-Weinberg, generations later. These cats have reproduced, the original cats have died, you have baby cats, they grew up, they had babies, they grew up, they had generations. I can't stress that enough with evolution. Generations. And let's say you went back and generations later, what you can see, you have 14 white cats. Black, you have 36 out of a population of 50. So now we do the same exact thing again and we go, okay, 14 out of 50. Let me go back to my calculator. 14 divided by 50 equals 28.28. So I come back here and I'm going to say, okay, Q squared equals 0.28. Let me take the square root of 0.28. Cannot do this in my head. So I'm back here, 0.28, square root of 0.28. We're going to round again, 0.53. 0.53. So this is Q. .53. So then I come back to P plus Q, P plus 0.53 equals 1, P equals 0.47. So here's where your flag goes up. You went from this to this. There's a decrease in the percentage or frequency of the dominant allele. There's an increase because you went from 0.45 to 0.53. There's an increase in the recessive allele. Your population is changing. Change over time. That is the basic fundamental definition of evolution. Change in a population over time. This population of cats is evolving. Now, why is it evolving? Look at the population. There are 5 factors that lead to evolutionary change. Which of those 5? We don't know. You would have to study the population further. This is just a tangible way to measure evolutionary change. It's quantifiable. It's scientifically provable by looking at allele frequencies to say this is a change in the population. 20 years. That might only be 20 generations. That's not a lot when we talk about evolutionary time. You want to study evolutionary time, can you watch this population for 10,000 years, 50,000 years? What kind of changes would we see there? Okay, so this is one way to work with the allele frequencies. Now, the other way, let me get this out. The other important thing to be able to do is work with those genotypic frequencies. Okay, so remember, genotypic frequency. We're working with this equation. All right, p squared plus 2pq plus q squared equals 1. So let me get rid of this. Oh, I killed myself here. Let me redo all this. P squared plus 2pq plus q squared equals 1. All right, so again, remember what each of these things represents. P equals your 2 dominant alleles. 2pq is your heterozygote. Q squared are your recessive alleles. And darn auto formatting. All right. Okay, so now over here, we've been given, let's say we've been given P, 0.4. So P is an allele frequency. And we're trying to figure out genotypic frequencies. Well, a couple ways to start this. If I know P and I want to figure out big A, 0.4 squared. 0.40 squared. So again, I'm going back to my calculator. 0.4 squared, or 0.4 times 0.4, 0.16. So P squared in this world, I'm going to put these over here. P squared equals 0.16. I can assume 0.16 or 16% of the population has homozygous dominant alleles. Now I don't know how many are heterozygous. I don't know how many are homozygous yet. So I go, okay, I got P squared equals 16. I still need to know 2pq and q squared. So let's start with a simple one. P plus Q equals 1. So 0.40 plus Q equals 1. Can everybody solve for Q? Should get 0.6. If I want to know Q squared, 0.6 squared. So we can come back here, 0.6 times 0.6, 0.36, Q squared, 0.36, P squared plus 2PQ plus Q squared equals 1. So you can do it a couple ways. You can say, okay, 0.16 plus 2PQ plus 0.36 equals 1. Do the basic algebra, 2PQ, subtract 0.36 and 0.16 from each side. So 1 minus 0.36 minus 0.16 equals 0.48. Okay, so if you add all three of those up, 0.16, 0.48, 0.36, you get 1. So now we know the frequency of each genotype within the population. So we can work all of this from the original starting point of just knowing how many recessive individuals are in your population. That is the power of Hardy-Weinberg, to be able to work through this equation, or both of these equations. The genotypic equation and the allele frequency equation. Generally, this is our starting point right here. I said I can look at this population and tell you how many white versus black I see, and from there, everything else is just basic algebra. All right, so hopefully this helps clear up Hardy-Weinberg. It is an equation you will need to recognize and be able to understand the basics of. You will use this as you move on, not just in this course, but in future courses. You're going to be expected to work the basic algebra behind Hardy-Weinberg to understand, is a population changing? That is a signal evolution is occurring.